The objective of this investigation is the baseline assessment and physical recovery of a Yokosuka D4Y airframe, originally built as a D4Y1 Judy, later represented in D4Y3 form for ground operations. Left abandoned at Babo Airfield in West Papua, the airframe sat exposed in an equatorial jungle environment for nearly half a century. Recovering an aircraft from a remote, hostile environment begins with a hard inventory of what still physically exists on the ground. Time matters, but the governing constraint at Babo is a deliberate mechanical deficit created before abandonment. Ground damage during attacks left the machine unserviceable, and once field repair was no longer possible, it crossed a one-way threshold. From that moment, it was no longer an operational asset, it became a static supply source. And what survives is defined as much by wartime stripping as by decades in the jungle. The Imperial Japanese Navy Air Service operated the D4Y1 out of isolated island bases where logistics were heavily interdicted by Allied air superiority. Under these conditions, ground crews cannibalized disabled airframes to keep the remaining fleet flying. Field stripping fundamentally alters the original configuration of the wreck. At Babo Airfield, ground crews often strip disabled airframes for usable components, severing electrical, hydraulic, and structural connections to extract high-value hardware. The most critical loss to this specific airframe was the complete detachment of its power plant. The D4Y1 was originally designed around an Aichi Atsuda 12, a liquid-cooled inverted V12 engine. When the airframe sustained its crippling damage, mechanics decoupled the engine mounts, severed the coolant lines, and hoisted the entire V12 block out of the nose. The heavy engine was subsequently discarded in the nearby tall grass, separate from the main fuselage. This action likely shifted the center of gravity of the remaining hulk. Without the massive forward weight of the 12-cylinder engine, and with decades of soft ground and corrosion working beneath it, the airframe slowly settled until the landing gear finally failed. Cannibalization left only a partial shell, a selectively scavenged skeleton rather than an intact machine. The forward engine bearers end abruptly in empty space. The cowlings that once streamlined the liquid-cooled block are either missing or crushed. Every mechanical linkage that once connected the cockpit controls to the forward motive section has been cut or forcibly detached. At Babo, wartime stripping was executed fast, with hand tools and under the pressure of repeated raids. Crews cut for speed rather than preservation. Hoses were slashed instead of unthreaded, wires were clipped instead of unpinned, and structural mounting points were sacrificed rather than protected. That choice left the forward firewall and engine truss torn and incomplete, complicating any later engineering effort to stabilize or rebuild what remained. The aircraft's physical footprint changed permanently when the 12-cylinder block was hauled away and discarded in the weeds. What remains in the revetment now sits nose-light on soft ground, taking slow, uneven static loads it was never designed to carry. The task is to extract the abandoned D4Y1 from the jungle and make it safe for controlled ground operation, despite a nose left mechanically incomplete and a structure already weakened by combat damage and wartime stripping. From here, the recovery is constrained less by intent than by material reality. What decades of heat and humidity have done to the aluminum itself. The molecular geometry of the primary aluminum structure imposes a hard limit on the restoration of the D4Y1. The constant high humidity and intense heat of the West Papua swamp act as a persistent corrosive bath. The aircraft was subjected to 50 years of this specific equatorial environment. It is not merely a matter of surface weathering or accumulated dirt. The mud and decaying vegetation trapped moisture against the metal, preventing the internal sections from ever fully drying out. The resulting chemical degradation permanently altered the material properties of the airframe, dictating exactly what can and cannot be done with the surviving wreckage. The primary constraint centers on the main wing spars. These heavy aluminum extrusions form the central load-bearing spine of the aircraft. They are engineered as the primary load path between wing and fuselage, absorbing lift, weight, and the extreme vertical forces generated during aerodynamic flight. However, aluminum airframe alloys of the era, especially where moisture is trapped and where steel fittings meet aluminum, can deteriorate rapidly when kept wet for decades. The swamp mud acts as an electrolyte, driving pitting and crevice corrosion, and, where dissimilar metals are in contact, galvanic attack. This continuous exposure erases structural margin long before the damage looks dramatic from the outside. In susceptible aluminum alloys, corrosion can advance along grain boundaries beneath intact-looking surfaces, intergranular corrosion that may remain invisible until strength is already lost. As corrosion products expand, they can drive layered, leaf-like exfoliation from within, collapsing tensile strength in the main spars below any safe tolerance for flight loading. That mechanism establishes the hard boundary for this project. The surviving structure can be stabilized and conserved, but it cannot be returned to the aerodynamic forces of flight. The degradation is uneven across the airframe. Water pooled in the lowest structural points, particularly the lower spar caps, the wing roots, and the belly bulkheads. In these areas, the corrosion completely flaked away the original material thickness. It altered the physical dimensions of the structural components, turning solid aircraft-grade metal into brittle, chalky layers. The recovery team must handle the remaining structure as a highly fragile shell. The load paths designed to handle flight dynamics can now barely support the static weight of the airframe itself. Assessing the wreck requires understanding that surface appearance is entirely deceiving. A section of outer aluminum skin might look relatively intact while the underlying structural stringers and attachment brackets crumble under slight mechanical pressure. Any lifting or handling plan must account for these hidden internal weaknesses. Applying tension to the wrong section of a corroded bulkhead will cause immediate structural failure, tearing the historical artifact apart. What matters now is not how it looks, but where it will tear. The swamp stripped factory coatings and oxidized the outer skin, erasing most painted markings and tail codes and blurring the aircraft's immediate visual identity. With those exterior identifiers gone, confirmation had to come from protected interior stamps, stencils, and data plates. Evidence that could be documented without grinding away fragile metal. Researchers Jim Long and Jim Lansdale assumed the task of confirming the exact origin of the airframe. Because the aircraft had been stripped of its engine and heavily scavenged by ground crews, many standard identification points were missing or destroyed. They had to systematically search the remaining internal structure to locate the original manufacturer data plates. These small aluminum tags, riveted to the interior framing at the factory, were designed to record the serial number, production date, and assembly location. However, prolonged exposure to the swamp moisture had heavily oxidized these metal plates, obscuring the stamped characters under thick layers of chemical buildup. To recover the information, the researchers relied on careful, non-destructive documentation of protected interior identifiers, surviving stencils, stamped fittings, and any remaining tags. Manufacturing impressions can survive even when surfaces are oxidized because the metal beneath a stamped mark retains a measurable depth profile. Instead of aggressive cleaning, the work depends on controlled lighting, macro photography, and repeatable imaging that can reveal faint depressions without grinding away fragile evidence. Long and Lansdale applied these precise decoding techniques to the degraded tags recovered from the jungle wreckage. They successfully extracted the hidden digits from the oxidized aluminum. To ensure accuracy, the researchers utilized a secondary verification loop. They cross-referenced the stabilized data plate numbers against surviving, severely faded factory stencils found on protected interior fuselage components that had escaped the worst of the ambient moisture. Taken together, the interior tags and protected stencils produced a best-supported identification rather than perfect certainty. The most consistent reading pointed to a manufacturer number of 7,483, an airframe serial of 483, and a delivery date in February 1944. Those identifiers were sufficient to tie the wreckage at Babo Airfield to a Yokosuka-designed D4Y1 Model 11 in surviving production records, even as corrosion erased most exterior declarations. With the serial number 7,483 securely established, the parameters of the project shifted from forensic investigation to physical logistics. The researchers successfully mapped the history of the machine, but the physical artifact remained trapped in a low-lying jungle revetment. The forensic success highlighted the immediate physical vulnerability of the wreckage. The verified airframe was an immobilized, severely degraded structure lacking its forward motive mass. How does a recovery team extract a positively identified but highly fragile airframe from a remote swamp without causing catastrophic structural collapse during transport. The fixed internal dimensions of standard intermodal shipping containers dictate the absolute physical limits of recovering an aircraft from a remote environment. Before any extraction could begin in 1991, the salvage team had to assess the structural reality of the site. 18 years prior, in the early 1970s, expatriate Roy Worcester surveyed the Babo Airfield and photographed the wreckage. He documented the D4Y1 sitting deep in the mud with its right landing gear completely collapsed. By the time salvager Bruce Fenstermaker arrived to extract the airframe in 1991, the structure had degraded even further. The swamp offered no infrastructure, no cranes, no paved access, and no machinery to lift the aircraft intact. With no cranes, paved access, or heavy equipment, extraction had to be done by controlled disassembly. Rather than lift the fuselage as one piece and drive bending loads through weakened wing roots, the team separated the wreck into transportable modules, wings, tail surfaces, and fuselage sections using careful, low-force handwork. Once the airframe was reduced to modules, packaging became a strict geometry problem. Every section had to pass a standard intermodal door opening on the order of 2.34 meters, just under 8 feet, forcing careful orientation of the fuselage and the integrated wing center structure. Inside the box, nothing could sit directly on steel. The custom timber cribbing had to cradle curved surfaces and spread load away from weak bulkheads. Wing panels and tail sections were stood, angled, and lashed so the components could not shift. Any slack would turn ocean vibration into abrasion against brittle aluminum. In 1991, Fenstermaker secured the separated, heavily corroded pieces in steel freight containers, ending the aircraft's 50-year isolation at Babo Airfield. The transport containers safely bridged the ocean, depositing the raw, physical materials of the dive bomber into storage facilities in the United States. But breaking the aircraft into shipping modules also broke its continuity, leaving restoration to begin from disconnected, mechanically incomplete sections. What critical engineering choices are required to reconstruct an incomplete, mechanically compromised airframe when its original motive power is completely extinct? The ultimate decision in any aviation rebuild rests on a razor-thin trade-off edge between achieving aerodynamic flight and preserving historical integrity. To fly a severely corroded aircraft, engineers must drill out its original factory rivets and discard the compromised primary structure. To preserve the original aluminum, the machine must remain permanently bound to the ground. For nearly 2 decades after arriving in the United States, the disassembled wreckage remained in storage at a facility in Valle, Arizona. It was not until 2009 that the components were finally relocated to Chino, California for a full structural evaluation. The restoration team immediately faced the consequences of the environmental decay. The physical reality of the aluminum dictated their operational ceiling. At Chino, inspection confirmed the wing spars could not support flight loading without replacing primary structure, so the team committed to a taxi-only rebuild in order to preserve the surviving Yokosuka-era aluminum. Securing the structural preservation path introduced a massive mechanical deficit. The airframe still lacked a motive power plant. The original 12-cylinder inverted inline engine had been removed from the airframe during wartime. Replacing it with an identical Japanese inline block for dependable operation was not a supportable path, given the scarcity of serviceable examples and the absence of a reliable parts pipeline. Instead, the Chino team pivoted to a cross-variant engine substitution. This involves adapting an airframe designed for a liquid-cooled inline engine to accept an air-cooled radial engine. The later wartime D4Y3 variant utilized a radial power plant, but 0 surviving examples of that specific model remained in existence. To bridge this gap, engineers selected an American Pratt & Whitney R-1830 twin WASP radial engine. This 14-cylinder power plant offered reliable operation for ground tests and closely matched the dimensional profile required to simulate the extinct Japanese radial variant. However, an air-cooled radial operates on entirely different mechanical principles than a liquid-cooled inline block. It requires direct external airflow over its cylinder fins to prevent overheating rather than relying on a closed liquid radiator loop. Mounting the American radial on an airframe built for an inline engine reopened the center of gravity problem. A radial engine concentrates a massive amount of weight in a very short physical length. In contrast, an inline engine distributes its mass over a longer, narrower footprint along the nose. If the new radial engine were bolted directly to the original firewall, the concentrated weight would sit too far back toward the wings. This would shift the overall center of gravity dangerously aft. An aft shift makes the airframe highly unstable on its landing gear, reducing weight on the wheels and creating a hazardous tipping risk during any ground movement. To correct this physical imbalance, engineers had to design entirely new structural motor mounts. They extended a custom steel mounting truss forward from the firewall, pushing the heavier 14-cylinder radial block further out into empty space. This calculated structural extension utilized mechanical leverage to match the original balance point. By moving the heavy mass forward, they ensured the static load transferred correctly through the structural bulkheads down into the main landing gear. Solving the internal mass distribution allowed the new engine to be structurally secured, but it created an immediate external clash with the original fuselage shape. The original airframe was contoured to wrap tightly around a slender, narrow block. How does a restoration team mechanically integrate a wide-diameter 14-cylinder radial engine into the narrow, forward geometry of an airframe without compromising the structural integrity of the fuselage? The decision to mount a 14-cylinder radial engine onto a narrow airframe forces an immediate geometry conflict at the firewall. The physical boundary of the substitute power plant significantly exceeds the original aerodynamic envelope of the dive bomber. The American Pratt & Whitney engine requires a wide circular inlet to provide direct cooling air over its finned cylinder heads. In contrast, the original Japanese sheet metal was tailored to tightly enclose a slender liquid-cooled block. To enclose the wider radial, the restoration team reshaped the forward cowl geometry by expanding sheet metal outward from the firewall and fabricating new aluminum panels that flared from the preserved cockpit lines to a circular intake. Because the engine sat further forward on an extended mount to meet center of gravity requirements, the cowl also had to be lengthened to cover the new mass and airflow path. The result was an operational housing that visually approximated the later D4Y1 radial silhouette, even though the aircraft would remain restricted to ground running. Enclosing the engine resolved the visual and spatial conflicts, but operating it introduced severe kinetic challenges. Starting a heavy radial engine attached to a historically compromised structure generates intense dynamic loads. The aircraft had to be engineered around a taxi-only envelope, landing gear, brakes, and fuselage attachment points tuned to absorb ground torque and continuous engine vibration without transmitting damaging resonance into permanently degraded wing roots. As the radial throttled up, rotational torque fed through the new steel mounts into aluminum bulkheads, and so reinforcement and load paths had to be controlled to keep twisting forces out of the spar carry-through. Braking geometry was equally unforgiving, enough authority to arrest momentum without pitching the nose into a propeller strike, and with operating limits on engine revolutions to prevent any lift-producing airflow over fragile wings. Cooling added a final hard timer. An air-cooled radial depends on forward airspeed, so taxi runs had to be short, monitored, and bounded by rising cylinder head temperatures. In 2013, those constraints were validated in public during the Plains of Fame airshow season in California as the engine started, the structure held, and the aircraft taxied under controlled throttle and asymmetric braking down the flight line. The aircraft now survives as a stabilized hybrid, authentic, an environmentally degraded original structure aft, and a deliberate forward simulation built to operate within strict ground limits. As this unique machine continues to operate within its strict ground boundary, how will future conservationists maintain an airframe that permanently bonds a running American power plant to the fragile footprint of an extinct Japanese design?